faithfully sharing insights and exploring great books from around the world. Hi, this is Sally's Book Talk. Today I'll be interpreting the book Knowing the Numbers for you. Math is everywhere in life. Homemakers balancing groceries, urban professionals managing mortgages and finances. Smart folks use math to boost efficiency and gains. So, what insights has math sparked for you? Feel free to share your thoughts in the comments. Knowing the Numbers. The author of this book is Professor Liu Shuifeng from Beihang University. Professor Chao Jiannang from Hong Kong Polytechnic University highly recommends it. He said, I meticulously read the entire book and gained immense insights. The book has 3 parts: thinking, methods, and learning. Through 18 anecdotes, the author links everyday routines with math concepts, showing how math enhances life. I've grouped these stories into 4 modules to explain: probability in everyday life, how to handle trade-off dilemmas, how to simplify complex problems and apply system science in daily life. And now I'll walk you through each one step by step. First, let's discuss probability in everyday scenarios. Let me start with an example. There are 2 people, Xiao Wang and Lao Li. Xiao Wang comes from a well-off family and, after college, didn't want a 9-to-5 job. So he launched a small travel agency with some like-minded classmates. In his scenic hometown, he built several homestays focused on leisure getaways. Although Xiao Wang and his wife were very diligent, their venture didn't go smoothly. Beyond fierce competition, the pandemic meant few city visitors came, so the agency had expenses but no income and soon couldn't sustain. Even with the partners' repeated efforts to grow the business, things backfired and the homestays failed. Now, consider Lao Li. He's always non-confrontational, an easygoing guy who believes fate controls everything. But his luck was poor. First laid off, then lost money on a small business. As he aged, health problems mounted. These 2 adopted different approaches to life. Lao Li's worldview is fatalism. Everything is destined, no effort needed. While Xiao Wang's worldview is struggle theory, believing effort can achieve anything. In reality, many world events are random. Starting a travel agency and succeeding is random, and turning a small business profitable is too. So the mathematical theory that studies random events is called probability theory. When facing many life challenges, you need a probability mindset. This worldview, called probabilistic worldview, advocates calmly accept reality, diligently change probabilities. Accepting reality means that, as random events, both success and failure are possible. If something undesirable happens, accept it. The meaning of this worldview lies in the latter part, diligently changing probabilities, which has 2 layers. First, acknowledge probability. Before doing something, face its randomness and analyze how likely success is. This can be figured out by summarizing cases of success and failure. For something with a low success probability, you must analyze it very carefully before taking action. For example, in today's China, travel agencies are everywhere, and homestay tourism isn't new. For Xiao Wang starting a homestay travel business now, competition was already fierce, and with the pandemic impact, the success probability dropped even lower. Second, you need the awareness and measures to change probabilities. The probability of an event can be altered by conditions, meaning you can create circumstances to boost success odds. For instance, Lao Li could increase revenue by improving service quality, product standards, or selling unique goods. Well, now let's circle back to probability. Probability is the foundation of hot topics like artificial intelligence and big data theories. This math branch originated from gambling, specifically roulette, a common game where a wheel is evenly split into 38 sectors, with numbers 0 to 37 randomly assigned.
Gamblers spend 1 yuan to buy a ticket with a number between 0 and 37, then casino staff spin the wheel.
When the wheel stops, the number at the 12 o'clock position is the winner. If your ticket matches, you win. The prize is 36 yuan, known as 36 to 1 odds. The question we're exploring is how this 36 was designed. With a wheel divided into 38 equal sectors, Only one number wins each time, so the gambler's win probability is 1 in 38, about 26.3% per thousand.
Suppose Xiao Zhang spent 1,000 yuan to buy 1,000 lottery tickets, won 29 times, meaning his winning frequency is 29 per thousand.
Note, this is called frequency. Also, Xiao Chen bought 500 tickets, won 12 times, so his winning frequency is 24 per thousand. Obviously, Xiao Zhang made money. While Xiao Chen lost money, in probability theory, there's a fundamental law called the law of large numbers. It says that as the number of trials tends to infinity, frequency tends to probability. This is a conclusion drawn from long-term practice. According to this law, whether it's Xiao Zhang or Xiao Chen, as long as they keep gambling, their winning frequency will fluctuate around 26.3% per thousand. The probability of winning in roulette is 1 in 38, meaning on average, a gambler wins once every 38 rounds. In other words, spending 38 yuan to buy tickets wins once, getting 36 yuan but losing 2 yuan, and that 2 yuan is taken by the house. Why isn't it 38 to 1 odds?
Because on average, a gambler wins once every 38 bets. If the house pays you 38, how can the house make money? Why not 34 to 1?
Because the odds are too low. It would discourage gamblers' enthusiasm. Generally, when designing gambling, the house sets their guaranteed profit at 5% to 10%. Sometimes even local governments intervene in the profit ratio. 36 to 1 odds mean you lose only 1 yuan if you lose, but win 36 yuan if you win, so it attracts many to try their luck. But gambling is meticulously designed. The law of large numbers tells you that long-term gambling leads to loss, so it's best to stay away. Probability isn't just in casinos, it's everywhere in life. Let's share a true story. One day, General Motors in the US received a complaint from a customer who said his Pontiac car discriminated against vanilla ice cream because he drove it to buy ice cream. Whenever he bought vanilla ice cream, the car wouldn't start, but it started fine when he bought other flavors. He wanted to know why the Pontiac wouldn't start every time with vanilla ice cream. Although General Motors thought the complaint was ridiculous, they still sent an engineer to solve the problem. The engineer drove the Pontiac to buy ice cream very seriously. The first night, he bought chocolate ice cream, and the car started normally. The second night, he bought strawberry ice cream, and the car started normally. The third night, he bought vanilla ice cream, and sure enough, the car wouldn't start. Coincidentally, a survey in London found that when taxi drivers wore leather jackets, the city's car accident rate increased. Some analyzed that leather jackets might affect driving, leading a legislator to propose banning them for taxi drivers. The bill nearly passed. Both cases involve causality issues.
Was vanilla ice cream causing the car not to start?
Were leather jackets causing more accidents? The GM engineer was thorough, meticulously documenting all 3 ice cream purchases and visiting the shop. He found vanilla purchases took the least time. Being popular, the owner pre-made several, while other flavors required on-the-spot preparation, causing longer waits. The car actually had a flaw called vapor lock. After shutting off, restarting required a cooling period. Too short a time prevented ignition. Once fixed, the car worked and vanilla ice cream was exonerated. In London, drivers wore leather jackets in damp weather when roads were slicker, leading to more accidents. Thus, accidents weren't related to leather jackets. Let's use the leather jacket case to explain misjudgment through probability theory. Its 3 events are involved. Damp weather is the cause. Jackets are worn for moisture protection. Increased accidents. Damp weather is the cause. Jackets are worn for moisture protection. And 88 jackets are worn. Thus, both jacket wearing and accidents are effects of dampness. No causality exists between them. To verify this, a study first examined the accident probability in damp conditions, then the probability when drivers wore jackets in damp weather. Both probabilities were nearly identical. This eliminated jackets as a cause. Probabilistically, jacket wearing, and increased accidents are independent events. Though independent, they share no causal relationship. But they often co-occur. Probability theory uses correlation to describe mutually influential events. In other words, drivers wearing leather jackets and increased traffic accidents are correlated events, which often occur together. And they share a common cause, but does the same cause always lead to the same outcome? Not necessarily. This brings us to the ABC theory of causality. For example, when a child gets poor exam results, their parent hits them. The cause appears to be the poor grades. The effect is the hitting, seemingly straightforward causality, but in many families, poor grades don't lead to hitting. An American psychologist explains this with ABC theory, where A is antecedent, B is belief, C is consequence. He argues outcomes are influenced not just by causes, but also beliefs. It leads to C through B. Some parents advocate persuasive education so they don't hit. Others practice corporal punishment so they hit. Same cause, different beliefs yield different outcomes, and beliefs exist independently. Thus, for good outcomes, beliefs are crucial. They shape human cognition. So, what was the legislators' belief about jackets and London accidents? They believed accidents were solely drivers' fault, ignoring environmental factors. Empathizing with drivers, this illustrates probability theory in life. It teaches us most world events are uncertain. Sequential events may lack causality, and even when causal, beliefs can alter outcomes. This is the essence of probabilistic worldview. Next, let's explore the mathematics of compromise. What is compromise? The term originates from Confucius's praise of Emperor Shun, of Yao Shun Yu fame, whom he revered for retaining the bad, promoting the good, balancing extremes, and serving the people. Its common meaning is compromise, avoiding extremes. Consider this example. A publicly traded company announced 2015 to 2021 profits in 2021, 1 billion in 2015, 940 million in 2016, 1.6 billion in 2017, 1.7 billion in 28, 1.2 billion in 29. 1.4 billion in 2020. Investors surely care about its 2020 to 2022 trajectory. If we take years as the x-axis and profits as the y-axis, then these 6 numbers become 6 points on the coordinate plane. From the first to the second point, it's a drop, then it increases afterwards, and the growth accelerates. To understand the company's profit growth pattern, person A constructed a fifth-degree polynomial whose graph passes exactly through all 6 points. However, using this polynomial to predict 2021 profits would show a cliff-like drop below 800 million yuan, and it would keep falling afterwards. Clearly impossible. Confucius said, "Hold the two extremes and use the balanced middle." If we take accurate description of the past as one extreme and reliable prediction of the future as the other, then this fifth-degree polynomial clings only to describing the past, ignoring the future prediction and so naturally misses the balanced middle. Clearly, this approach violates Confucius' teaching, especially since for investors, predicting the future matters more than describing the past.
Generally, a company's annual growth rate stays similar, so a linear model is more scientific.
Here, with 6 points on the plane, randomly choosing 2 to draw a line gives 15 possible lines. Which line is best? If you pick 2 points for a line, the other 4 likely won't lie on it. These points have vertical distances to the line, positive or negative. Squaring these distances eliminates sign issues, giving 4 squared errors. The line with the smallest sum of these squares best represents all 6 points. Later, someone thought, why require passing through 2 points? What if a line minimizes the sum of all 6 squared errors without passing through any point? Wouldn't that be better? This idea is least squares regression. It prioritizes minimizing total error over fitting points, embodying Confucius's balanced middle philosophy. This least squares method was first proposed and used by the great mathematician Gauss. On New Year's Day, 1801, Astronomer Piazzi discovered a new asteroid, naming it Ceres, and tracked it for 40 days, recording data. Hmm. Uh, Afterwards, the star vanished in the blazing sunlight. Astronomers then knew planetary orbits were elliptical with the sun at one focus. Ceres and Earth weren't coplanar, making trajectory predictions difficult. Many astronomers gave estimates for when it might reappear. But the elusive Ceres remained hidden. That year, 24-year-old Gauss used Piazzi's data and least squares to estimate Ceres's orbital ellipse. In early December 1801, he predicted it would reappear by month's end, providing location estimates. Sure enough, two astronomers observed Ceres in Gauss's predicted area on December 31st, 1801, and January 2nd, 1802, making Gauss instantly famous. 886. Least squares abandons perfect historical fitting to focus on future estimation. That's mathematical modeling's true essence. Least squares integrates with probability, for example, estimating 2021 profits while calculating probabilities and 95% confidence intervals, 95% certainty of profit ranges. It also pairs with recursive algorithms, updating formulas with new data without restarting, mirroring step-by-step strategies. That concludes the mathematics of compromise. We know the world is both complex and simple. Complex because its manifestations are intricate, colorful and ever-changing. Simple because underlying principles are fundamental. Systematic breakdown reveals elemental combinations. Seeing simplicity and complexity requires skill. For part 3, let's discuss mathematical simplification methods. In mathematics, decomposition simplifies complexity. Middle schoolers know prime factorization and polynomial factoring. This decomposition tech has countless real-life applications. Of course, modern tools like smart bands, tracking your steps and distance, use far more complex decomposition than basic factoring. What's the principle behind this? Smart bands contain an accelerometer that detects arm motion velocity changes, storing the detected signals. These signals mix walking-related data with irrelevant motions like dressing or grabbing objects. Normal walking is periodic. If we extract this periodic motion from chaotic signals, we isolate walking from other activities. Mathematics provides decomposition via Fourier analysis, breaking functions into sinusoidal wave combinations. By counting sine waves matching human gait patterns, we get step counts. The chip performs Fourier decomposition, counts steps, and converts wave width to stride length for distance. Similarly, complex tasks are difficult to handle whole, so we decompose them into smaller subtasks, creating specialized devices for each. Computer chips, or processors, exemplify this. The CPU, Central Processing Unit, handles all computations on the motherboard. The GPU, Graphics Processing Unit, manages displays on the graphics card. Even with advanced chip tech, CPUs and GPUs remain separate, each executing specialized tests efficiently. Modern AI computers add a third processor, TPU, Tensor Processing Unit. Each handles distinct functions. TPUs specialize in deep convolution calculations. More specialized means more powerful for targeted tasks. AlphaGo's core was TPUs, enabling its undefeated Go mastery. When decomposing tasks, each subtask is a dimension, like computation, display, and AI processing. Three-dimensional task decomposition. With many possible decomposition dimensions, what's the optimal choice? Professor Phillips from Columbia University conducted a study. He designed a serial murder case and formed 3 investigation teams, giving all case materials to them simultaneously to analyze and solve. Group 1 was a single renowned expert working alone. Group 2 consisted of several investigators with similar backgrounds who knew each other. Group 3 comprised specialists with diverse skills who were strangers. Results showed Group 3 had 75% accuracy. Group 2 achieved 54%, while Group 1 only 44%. Why did the team of specialized strangers perform best?
Let's explore the mathematical principle. 2 intersecting lines on a plane meet at a point.
If you shift one line parallel, the intersection point moves. Notice that when the angle between lines is smaller, the point moves farther. safely sharing insights and exploring great books from around the world. Hi, this is Sally's Book Talk. Today, I'll be interpreting the book Knowing the Numbers for you. Math is everywhere in life. Homemakers balancing groceries, urban professionals managing mortgages and finances. Smart folks use math to boost efficiency and gains. So, what insights has math sparked for you? Feel free to share your thoughts in the comments. Knowing the Numbers. The author is Professor Lu Shuifan from Beihang University. Professor Chao Jianlong from Hong Kong Polytechnic University highly recommends it. He said, I meticulously read the entire book and gained immense insights. The book has 3 parts: thinking, methods, and learning. Through 18 anecdotes, the author links everyday routines with math concepts, showing how math enhances life. I've grouped these stories into 4 modules: probability in everyday life, how to handle trade-off dilemmas, how to simplify complex problems, and system science in daily life. Now, I'll walk you through each one step by step. First, let's discuss probability in everyday scenarios. Let me start with an example. There are 2 people, Xiaowang and Lao Li. Xiaowang comes from a well-off family and, after college, didn't want a 9-to-5 job. So, he launched a small travel agency with some like-minded classmates. In his scenic hometown, he built several homestays focused on leisure getaways. Although Xiaolong and his wife were very diligent, their venture didn't go smoothly. Beyond fierce competition, the pandemic meant few city visitors came, so the agency had expenses but no income and soon couldn't sustain. Even with the partners' repeated efforts to grow the business, things backfired and the homestays failed. Now, consider Lao Li. He's always non-confrontational, an easygoing guy who believes fate controls everything. But his luck was poor. First laid off, then lost money on a small business. As he aged, health problems mounted. These 2 adopted different approaches to life. Lao Li's worldview is fatalism. Everything is destined, no effort needed. While Xiaowang's worldview is struggle theory, believing effort can achieve anything. In reality, many world events are random. Starting a travel agency and succeeding is random, and turning a small business profitable is too. The mathematical theory that studies random events is called probability theory. When facing life challenges, adopt a probabilistic worldview, advocating calmly accept reality, diligently change probabilities. Accepting reality means acknowledging both success and failure as possible random outcomes. When undesirable results occur, accept them. The worldview's core lies in the latter part, diligently changing probabilities, which has 2 meanings. First, acknowledge probability. Before acting, confront randomness and analyze success likelihood. This can be determined by examining success and failure cases. For low probability endeavors, thorough analysis is essential before proceeding. For instance, in today's China, travel agencies abound and homestay tourism is commonplace. Xiaowang, starting a homestay business, now faced intense competition. Pandemic impacts further lowered success odds. Second, develop awareness and measures to change probabilities. Event probabilities can be altered by conditions, creating circumstances to boost success chances. For example, Lao Li could boost revenue by improving service quality, product standards, or selling unique goods. Now back to probability. Probability forms the bedrock of hot fields like artificial intelligence and big data. This math branch originated from gambling, specifically roulette, a common game where a wheel is evenly split into 38 sectors with randomized numbers, 0 to 37. Numbers are randomly assigned to sectors. Gamblers pay 1 yuan for a ticket with a number, 0 through 37. Then, casino staff spins the wheel. When the wheel stops, the number at the 12 o'clock position wins. Matching tickets win. The prize is 36 yuan, known as 36 to 1 odds. We're exploring how this 36 was determined. With 38 equally probable outcomes, win probability is 138 out of 38, approximately 26.3% per thousand. Oh, well. Suppose Xiaozhong spent 1,000 yuan on 1,000 tickets, won 29 times. His win frequency is 29 per thousand. And note, this is frequency. Xiao Qian bought 500 tickets, won 12 times, frequency 24 per thousand. Clearly, Xiao Zhen profited, while Xiao Chen lost money. Probability theory has a fundamental law, the law of large numbers. It states that as trials approach infinity, frequency converges to probability. This conclusion stems from long-term empirical observation. For this law, whether Xiao Zhang or Xiao Chen, if they keep gambling, their win frequency will fluctuate around 26.3% per thousand. Roulette win probability is 138%, meaning, on average, a gambler wins once every 38 rounds. Spending 38 yuan wins once, yielding 36 yuan. A 2 yuan loss kept by the house. Why not 38 to 1 odds? Because if the house paid 38 yuan per win over 38 bets, they'd earn nothing. Why not 34 to 1? Because lower odds would discourage gamblers' participation. Generally, when designing gambling games, the house sets a guaranteed profit margin of 5% to 10%, sometimes even regulated by local governments. And 36 to 1 odds mean losing just 1 yuan if you lose, but winning 36 yuan if you win, attracting many to try their luck. But gambling is meticulously designed. The law of large numbers proves long-term gambling leads to loss, so it's best avoided. Probability isn't just in casinos, it's everywhere. Here's a true story. One day, General Motors got a complaint. A customer said his Pontiac discriminated against vanilla ice cream. It wouldn't start when he drove to buy it. Oh. For example, in the 19th century, U.S. railroads pioneered container shipping. Pack goods in containers, load them onto flatbeds, unload at stations, and reuse the flatbeds, dramatically boosting rail capacity. Around the 1960s, this concept moved to shipping with container vessels. Previously, cargo was loosely stacked and hauled, making loading or unloading extremely cumbersome. Container ships stack containers on deck, slashing handling time and enabling seamless ship-rail transfers. This seemingly small shift from bulk to containers revolutionized modern shipping. And now consider high-voltage electricity. Daily single-phase power is 220 volts. Industrial, just 380 volts. So why have 22,000 volts or higher lines? Substations step up voltage at power plants and step down at users. Why? To cut transmission energy loss. Equipment has fixed rated voltages. For example, three-phase motors run at 380 volts where horsepower depends on current. But power travels via tables with resistance from distant plants. And when current flows through cables, heat loss equals current squared times resistance. Thus, higher current means more energy loss. Since power equals voltage times current, boosting voltage reduces current for fixed power. User end voltage is fixed, but transmission voltage isn't. So higher voltage minimizes loss. 1/4. So when transmitting electricity, we boost voltage 100-fold, reducing current to just 1% of original. Papal energy loss becomes 1/10,000th. Savings are enormous, justifying substation investments. Today we live amid transformations. That broadband modem in every home, short for modulator demodulator, converts fiber optic digital signals to analog for your phone. So when facing life challenges, try shifting perspectives. A transformation might solve problems unexpectedly. Math permeates life, yet many miss it. Abstracting mathematical problems and applying solutions boosts efficiency and smooths workflows. After today's discussion, what new math insights do you have? Feel free to share your thoughts in the comments. While knowing the numbers, that concludes our book interpretation. Show notes are below the audio. Until next time.